Hello guys, this is the second PowerPoint in the coasts unit. Hope you're well. Hope you're getting lots of productive stuff done in this time off. So this PowerPoint's all about landforms and landscapes along the coast. And basically what we're going to be looking at is we're going to be defining what is a landform, what is a landscape, because they're quite different things. We're going to be looking at some examples of some, and then we're going to be going through some other things such as what causes the tides, what causes tidal fluctuations around the country. It should be quite interesting. So let's get stuck in. So what is the difference? You can see you've got two pictures here. They've both got a range of coastal land forms in them, but they are both one landscape. So a landform is a feature along the coast. Say for example the picture on the left, you've got lots of stacks and stumps out in the sea, and you've also got a beach. Those are all landforms. The landscape is the whole coastline that those are within. So from one side of the picture to the other is the landscape, and the different features you can see within it are the landforms. Picture on the right, you can see you've got a little bay there. That's going to be your landform. You've got a headland either side of it, that's your landform, and then also you've got another headland jutting out into the sea, another landform, but the whole thing is a landscape. And we can class landscapes as high energy and low energy landscapes, and we'll come on to that in a little bit. So a coastal landscape then. Coastal landscapes are the big sections of the coast, like I said previously, and they include both erosional and depositional landforms or features. Now every landscape is different, so each will have a range of the two happening in it, and you can see the 5 bullet points there. We've got different things that are going to affect the landscape, so like for example the rock type, the climate, the different processes you've got going on there, the amount of energy that is there, and the amount of time that has been developed over. So have a read through them. Take some notes, add your own points in there. Right, so what we're going to do now is you're going to see a series of images and some questions at the side. And I want you to use your knowledge of the coasts to try and tell a bit about the story of this coastline. So using your eyes and your brain, think about things like the rock type, the climate, what marine processes are happening there. Is it erosion? Is it deposition? What types of erosion? How much energy has been input into the system? Is it a high energy system? Is it a low energy system? How can we tell? How old does the coastline look? And is it dominated by erosion or deposition? So what we'll do, I will give you a couple of minutes on each one. I'll stop talking, leave it 2 minutes, then I'll come back in and I'll talk through it, and hopefully my ideas match yours. If you need longer, obviously just pause it for longer and go through each of the questions. If you don't have a clue about this, just think, well, does it look like there's erosion? Does it look like there's deposition? Basically, for a high energy coastline, you'd expect lots of big waves, not much sand present, and then for a low energy coastline you'd expect the opposite, so small waves and lots of sand. So I'm going to leave it 2 minutes. I'm going to have a bit of my tea. You've got to have a cup of tea when you're doing this, and okay, just jot some notes down and we'll compare in a couple of minutes. Okay, so that's been about 2 minutes of me sat in silence. Lovely. So if we look at this, the rock type, hopefully you can see that it's quite hard rock, and there are signs that it is sedimentary rock. So for example, right in the middle of the picture, the sort of bit that juts out into the sea with the yellow on it, you can kind of see that the line goes out an angle just towards the end of the headland, and what's happened there is the rock's been laid down over time horizontally, and then as the tectonic plates have shifted and they've crunched together, that line has been distorted, and now it goes at an angle to the sea. So we've got some sedimentary rock there, but it's really old sedimentary rock that's probably been compressed, so it's quite hard and quite resistant. The climate in the area now, it looks like a kind of British maritime climate. And when I say maritime, just basically means sea. So a coastal climate. What that means is you're going to have lots of storms there, potentially lots of rainfall. So there's going to be lots of opportunities for both weathering and erosion. Marine processes. Now, you can see at the bottom you've got a wave cut platform at the bottom of the cliff. You've also got wave cut notches starting to form, and you have got some signs of faults in the rock. You can see again right in the middle, just to the left of the image, a little cave, which is a clear sign of erosion is going on. So you can look at that image and basically there's no beaches there, there's no signs of deposition, so it must be an erosional landform. How long has that been going on? Well, probably quite a while. This coastline's probably tens of thousands of years old. And yeah, is it dominated by erosion or deposition? Well, for this one, you can say it's safely say it's dominated by erosion. Okay, so another picture. Same things. What I want you to do, pause the video this time. I'm not going to wait 2 minutes. That's silly. Pause the video, answer the questions on the right, and then we'll go through and just unpause when you are ready to go. Okay, so if you look at this picture, you can see the rock type. Now we've got two types of rock here. We've got the white cliffs along the right hand side, and they're made of chalk, and that's really crumbly, really soft. This is actually in Dorset, so it's quite close to us, 100 miles or so along the coast. And you've got a big old beach formed there, so we've got signs of deposition already. We've got a really soft cliff, so that's going to be providing us lots of sediment. And then on the left of the picture, you've got an area of different rock, and that's resulted in the arch you can see there, which is known as Tidal door. And that arch is made of more resistant rock. I think it's limestone that's been deposited there. It's much more resistant than the white rock you can see on the right. And what that's resulted in is it's resulted in the little area of shelter around this arch, and that's why the beach is built up. If you look further away in the image along the white cliffs, you can see that actually there's not much beach in front of it, but then when you get close to the arch and the shelter, suddenly the beach is a lot more. So what can we tell about the climate? Well, you know what the climate's like in the southwest. It's quite wet, quite mild, so you're going to get a lot of processes, potentially a bit of freeze-thaw weathering in the winter, lots of water soaking down into the cliff, so you might get a bit of slumping, a bit of mass movement. Inputs of energy in sediment, or you can see the far image and the bit on the left, you've got signs of erosion, so that tells us that there's high energy going in there. But also you've got a source of sediment in the cliffs, which is going to be providing lots of sediment for that whole landscape. And if you remember back to lesson 1, the whole littoral cell. How long have these processes been going on? Again, this is a long old time. The cliffs that you can see are actually going to be quite young, but the arch on the left is going to be really old. When I say quite young, by the way, I mean like hundreds or thousands of years. Not like that arch is probably like 10,000 years old. Dominated by erosion or deposition, well, this is kind of a mixture of both. You've got erosion on the left, deposition in the middle, and then erosion on the right. So this coastline has got a lot going on in the space of about 400 meters. Third and final image. So again, have a look at the image, pause the recording, answer the questions on the right, and yeah, just have a go at that for a couple of minutes and hit pause. Okay, so we're gonna go through this now. So you can see this image, you can see quite far in this along the coast, and in basically the main image is a spit. So rock type, you can see in this area there's no big cliffs, there's no big headlands, so the rock type is going to be quite soft. The climate, again, British climate, so you're going to have high rates of rainfall, seasonal storms. Marine processes, the main marine process with a spit is longshore drift or littoral drift and deposition. And you can see that there's loads of sand there, so there's loads of deposition. You've got a big old mud flat in behind. We'll come on to those when we do spit, so don't worry if you're not sure what a mud flat is. You can also see that there's some human building on the end of the spit, and that tells us something about this area. It tells us it's quite stable because you're able to build and live on it. And you can see this, you can kind of see through the water just in front of it. It's quite a shallow area. Which tells us that there's not much energy because the waves, they'll break, basically the shallower the water, the further away from the shore the waves are going to break. So they're going to lose all their energy before they hit the coast, and you're going to get stuff building up. How long has this been going on? Well, spits don't tend to be very old. They tend to move and change quite a lot. So this one might be hundreds of years old. And is it dominated by erosion or deposition? Well, like I've just said, dominated by deposition, this one. So we've looked at some landscapes, we've analysed some landscapes. So what is a landform? Now, a landform is formed from either deposition or erosion. They're the smaller features, so for example, arch, wave cut platform, spit, it might be a beach, it might be a headland, a bay, a cove, a stack. They're all, though, outputs from the coastal system. And they are all the result of material being added or removed to the coastline. And remember, landforms form part of the landscape. It's really, really important that you're clear with the difference between a landform and a landscape. Okay, do not get these confused. Right, so here we have a diagram which I drew myself with my lovely art skills with all the different labels of the zones of the coastline. Now, like I said previously, this is important because in each zone different things are happening, and the name for a lot of it kind of gives it away. So we're going to start at the back with the back shore, which is BS. Okay, the back shore is the area of the beach that doesn't get reached by high tide. So if you think about the back shore, not much is actually going to be changing here. You might get a few plants starting to grow there. It might be the area of the beach where, say, large items of driftwood build up after big storms, but it's not reached by high tide. It will be reached, though, like I just said, by big storms. So for example, if you go to a local beach, I'm just thinking you've got Elbury Cove quite locally. If you go to Elbury Cove, quite often at the back of the beach, you'll see plants starting to grow on the pebbles, and there'll be some larger material there that's basically been there for ages because the sea doesn't reach it, the sea can't take it away, and the sea can't shape that area. Moving towards the sea, then we go to FS, which is the foreshore. That's exposed at low tide. So what we can expect from the foreshore is a mixture, really. So it's only going to be affected by marine processes whilst it's covered. It will be reshaped every high tide, though. So if you go to the beach some days, it will look very, very different to if you go on other days, and it's all to do with the amount of energy in the sea at high tide. So FS, the foreshore, does have quite a high rate of change in the landscape. There's quite a lot going on in the foreshore. The inshore is the next one, and that's the top label. So the inshore is basically anywhere from where the waves start to break inwards towards the shore. So if you're at the beach and you look out, you can see where the waves start to break, and that's where the wave cycles become interrupted. This is where, so the inshore zone is where erosion is going to begin, because the breaking of the waves is what causes the erosion. The offshore OS is the zone out to sea beyond the shore zone. Here you're not going to get much deposition, you're not going to get much erosion, because there's going to be lots and lots and lots of transportation going on in that zone. So offshore. Then we've got near shore, which is NS. That's the area between the low tide and the breaker zone. Now here you're going to get, again, a lot of coastal processes happening in NS. As the waves start to break, they're going to start to transfer their energy to the sediment. So they're going to either start to build up beaches or remove material, depending on how big the wave is, really. That's your NS. SWZ, sorry, is swash zone, and that's the area affected by the movement of water up the beach. So swash, remember, goes up the beach. So movement of water up the beach is going to push material up, and it's going to shape it. It's either going to cause to be a really steep beach or a really flat beach. Surf zone is the zone between low tide and the point at which waves start breaking. So again, here, this is where you're going to get quite white water. It's often the area that's, if you were walking out to sea, it would be the area where the waves would have broke by then. So again, there's going to be lots of energy, lots of turbulence there, lots of process going on there. And then the breaker zone, BZ, that's where the waves start to break. So like I said, the waves are cyclical. So if you look at the energy moving within a wave, it's circular. When that circle's broken, that's when the wave breaks. So from the breaker, basically from the breaker zone inwards, from the breaker zone up to the foreshore, that's where you're going to get most of your coastal processes happening. The backshore and offshore, not really much going on there. Again, try and familiarise yourself with these. Don't worry too much. I know there's a lot of terms in there. Don't look at these and go, oh, there's no way I'm going to remember all those. I'm not expecting you to remember all of them. Essentially, all you need to remember is from where the wave breaks to where the high tide line is. That's where most of your coastal processes are going to happen. So we're going to move on now to where does the energy come from. So we've looked at where the processes happen. We've looked at what the energy can cause, but where does the energy actually come from? So have a think back to the first lesson. What are the energy sources in the coastal environment? Say a few of them to yourself now. Hopefully you can remember, and then what we're going to do on the following slides is go through them one by one. Coolio. Okay, so the first source of energy we're going to talk about in the coasts is the wind. Wind's quite straightforward. It's the movement of air from an area of high pressure to an area of low pressure. Now, high pressure is formed by cold air when it sinks, and low pressure is formed by hot air when it rises. So what we usually find is that the land heats up quicker than the sea. So the land usually has a low pressure over it. The sea has cold air over it, which is under high pressure, and the cold air from the sea moves on land to fill the low pressure void left by the hot air. So wind is the movement of air from high pressure areas, usually over the sea, to low pressure areas, usually on land, and this is why it's usually windier at the coast than it is anywhere else in the country. Second source of energy at the coast is the waves. Now, waves are basically caused by the movement of the wind over the surface of the water, and the energy in the wind is transferred to the top layer of the water, and that is what causes the wave. So it's basically the friction as the air moves over the water. The air's kind of pushing, tickling, caressing, whatever you want to say, the water along. And that's why we get the waves, because the air is basically dragging the water along. Okay, so one thing to get your head around with waves is that the water doesn't actually move that far. So if you follow a wave from right out at sea into shore, the water particles you're following aren't the same. Imagine that they are like a slinky. If you hold a slinky apart at one end and you send a wave down it to the other end, the slinky's in the same position, but the wave has moved. So that's the way the waves work in the sea as well. Yeah, so essentially the waves caused by the wind. A little bit more about the waves here. So you can see some of the key terms on the left. The wavelength, which is the distance between the waves, decreases as you get closer to the shore, and you can see that on the diagram on the right. So the waves get compressed closer and closer together. The wave height also increases. That's because you can see in the diagram you've got the stack of 4 circles going around. If you look at them out at sea, they're quite low, but as they get close to land, they get pushed up, so the wave height actually gets bigger close to land. The wave steepness, that also increases as well, and you can see that the waves do get steeper in the diagram. When a wave breaks, it's essentially when that tower of water can no longer go around in a circular motion, so it collapses on itself. Imagine someone's riding like a unicycle and you suddenly stop the wheel from moving. What's going to happen is that slowly they're going to tip forward, or quite quickly, maybe, I don't know, they're going to tip forward and they're going to hit the ground. And that's basically what a wave is. It's like a giant stack of water riding on a unicycle, and then when the unicycle hits the bottom of the sea, which is the seabed, it's going to fall over and it's going to topple over. This is where the breaker zone starts. So you can see in the diagram, the third wave from the shore is just about to break, and the 2 waves closest to the shore have broken. And that shows you where the breaker zone starts. I hope my unicycle analogy was clear, by the way. It seems a bit stupid going back on it, but hopefully you got the point. Right, as I'm sure all of you know from GCSE geography, there's 2 types of wave. We've got destructive waves and we've got constructive waves. So we're going to talk about destructive waves for a couple of minutes. These are your waves that cause erosion. They are high energy waves. They've got high wave height. They've got a short wave length, so it means the wave hit quickly and closer to another on the shore. They form very distinctive landforms, but basically what they do is they remove material from a beach, and they're going to result in some very particular features. You can see in the diagram there, you've got a really steep beach just down from the breakpoint bar, and you've got a weird kind of like dip in the landscape. Now what's essentially happened is every time a wave hits, it's pushing the material further and further upwards at the top, and also scouring out material at the bottom, and that's why you get this really steep profile. If you've ever been to a destructive beach, so if any of you have been to Dorset, you've got Chesil Beach up there, it's quite a famous one. In Torbay, Elbury Cove is a destructive beach, that is quite a steep one as well. And also at Oddicombe, bottom of the Cliff Railway, the beach there is a destructive beach, gets really deep really quickly. So if you ever go to the beach and you see it looking like this, almost like mini cliffs in the coastline, that is called a breakpoint bar, and the breakpoint bar shows you where the waves are reaching, because what they're doing is they're basically digging out the material from the bottom of the mini cliff in the sand, if you like. So you can see an area all along the picture of darker sands towards the top, and that the bottom of that dark sand is essentially where the sand's being dug out from. And the reason that sand's dark is because it's collapsing down and it's still got quite a lot of its moisture content, so it gives it a different colour. So if you look at this coastline, you've got a really steep beach. Now this wouldn't be much good for tourists or anything like that. It's very destructive, and this is going to be, a lot of this sand is going to be being removed very quickly from the beach. So this is another beach formed by destructive waves. Again, you can see it's really steep. There's lots of evidence in here that is destructive waves. So the first one, on the left, you can see a strand line where that big piece of wood is, looks like a broomstick or something. And there's a line of seaweeds that goes all the way along it, and that tells us that's the last point that the sea was actually able to reach, because it's left loads of material there. A bit further up from that, you've got a berm. Now berms are formed usually in big storms, and you can see beyond that you've got a storm beach where there's loads and loads of material, like loads of twigs, loads of might be bits of glass, might be anything the sea's carrying, thrown up there, and it just stays there for a long period of time because the sea doesn't usually get that high. It's only during big storms. So the storm beach is just the material left behind basically beyond a berm during a big storm. So the berm shows us during that storm, that's basically how high the sea was, and that's how far the waves are reaching inland. Beyond that, you can see you've got patches of green where actually plants have started to grow, and if you've got plants growing there, it tells us that the sea doesn't reach there very often. So the plants have actually got quite a nice stable habitat for them. So if you ever go to the beach and you see this weird sort of mound, it's called a berm, and that's where the storm reached last time. And if you go over the berm, you'll usually see loads of older like abandoned material by the sea. So going on to constructive waves now, these waves are much flatter, they're much further apart, and they're much lower. Okay, so they've got what we call a longer wavelength. The wavelength, remember, is the distance between two waves, so the waves are much more spread out. They're lower, so they haven't got as much energy, and that means they're going to often deposit material. So you can see they've got a strong swash up the beach, deposits material, and then the energy back down the beach is very low, so it's not going to take much material away. Over time, you're going to end up with these lovely smooth beaches, and yeah, this is a low energy beach. Okay. So in this photograph, you can see lots of evidence that it's constructive waves that are happening here. Evidence number one, the waves are quite spread out. You've got a good couple of meters between each breaking wave. Evidence number two, loads of sediment there. And evidence number three is the beach is nice and flat. So you can just use your eyes and your brain and infer quite a lot about this landscape. What we can say is at the moment, that the waves are quite low energy, tells us that there's not much wind in the area, tells us that the landscape's going to be quite stable. You can see there's lots of vegetation around, but then in the background you've got some cliffs as well, so it might not be like that all the time. That's another key point to remember, is that coasts and waves can change. So for example, during a storm you get loads of destructive waves, but then most of the time you might have loads of constructive waves, so they can flit around. So don't think that one area's always got constructive waves or destructive waves. They do have both. Okay, another source of energy at the sea is the tides. We've got two types of tide on the planet in the coastal areas. We've got a semi-diurnal, which we have in the UK, which means basically we get 2 high tides and 2 low tides every 24 hours. And other areas are diurnal, so they only get 1 high tide and 1 low tide per 24 hours. Obviously, the more tides you have, the more different areas of the coast are going to be exposed to the seawater. So for example, if you imagine the area towards the top of a beach, if it's a diurnal area, it's only going to be covered up once a day, but it's going to be covered up for quite a long time. So there could be quite a lot of process happening there. Equally, a semi-diurnal area, it's going to have the sea coming in and out twice a day. So again, that's going to cause quite a lot of change in the coastal environment. Obviously, at high tide, more of the area is covered, so therefore the area can actually be acted on by the water. So tides are caused by the gravitational pull of mainly the moon, but also the sun to a much smaller extent. And we do have these occurrences called spring tides and neap tides. So you can see on the picture on the right, a spring tide occurred when the seawater is basically being pulled by an alignment of the sun and the moon, and what that's going to cause is it's going to cause a much higher high tide. So sometimes, for example, in Paynton, the tide's almost up to the height of Paynton Pier, and that's called a spring tide. So basically when the sun and the moon work together to pull the seawater up. And the opposite of that is a neap tide. That's basically when they counteract each other, and the tides are much smaller, so what you'll end up with is high tide and low tide will be much around the same mark, whereas at spring tide, the high tide and low tide are massively different. There's a huge range in it. So yeah, spring tides, obviously higher seas, more energy, more coast affected by the water, a bigger change in the coastline. Yeah, so spring tides, neap tides, try and familiarise yourself with those. Hopefully the diagram helps with that, but it's mainly the moon's force that will affect the tides. A tidal range is basically the difference between the height of the sea at high tide and the height of the sea at low tide. Some areas around the UK have got a really high tidal range, some have got a really low tidal range. As you can see from the map on the right hand side, the Bristol Channel, where the arrow is, that has got one of the highest tidal ranges in Europe. Essentially, because the land is shaped like a funnel, it amplifies the effect of the tide a lot more. And you can see your tidal range can be up to 14 meters. So that's ridiculously high, isn't it, when you think about it? 14 meters of water different between high tide and low tide. You can see Torbay, we're on about 4 to 5 meters difference between high and low tide, so it's almost 3 times the difference between ours. And then as you get up towards Norway and Sweden and Denmark up there, is below a meter, and that's largely because the water's much shallower there, so they've got a much shallower tidal range. Okay, so obviously the bigger tidal range, the more water you're going to have at high tide, so obviously the more energy, the more changeable the landscape's going to be. So this is a map of the Bristol Channel, which just shows you the funnel-like geography of the area, really. You've also got loads and loads of rivers discharging themselves into the Bristol Channel, which is obviously going to add to the amount of water you've got there. So any of those towns, so for example Cardiff, Newport, Weston-super-Mare, they're going to have a really high tidal range along those beaches there. To a lesser extent, like your Porthcawl, Swansea, Ilfracombe, Barnstable, that sort of thing along there. Okay, so ocean currents can also supply energy and sediment to a coastline. There's 2 types of ocean current. So we've got surface currents. These are driven by local wind patterns, wind variations, and the global wind systems. That's your air cells, things like that. And this goes down to a depth of about 400 meters to surface, and then beyond that you're in the deep circulation. Now obviously with climate change, the surface waters are heating up a lot more, they're transferring a lot more energy to the deep circulation, and it's kind of changing the patterns of ocean circulation. So that's something to bear in mind, is that climate change can actually deeply affect ocean currents, which long term could affect the supply of energy to a coastline. Deep circulation can provide things like nutrients, oxygen, heat to the surface, and the surface can provide the same to the deep water. So these two interact, but they're obviously, the deep water is a lot higher density. It kind of sits below the surface water, mainly because it's a lot colder. And if you remember from the water and carbon cycles thing with the latent heat, is that when something's colder, the particles are more organized within it. So from the ocean circulation, the energy from the water is transferred to the coast, where it's either going to cause erosion or deposition, depending on how much energy is transferred. A much smaller version of an ocean current is called a rip current. Now, any of you that have ever done like life-saving courses or anything like that, you might be familiar with what a rip current is. Now, rip current is on one particular part of a beach. You'll have an area where the water is flowing a lot quicker than in other areas, and you can see in the diagrams here what it looks like. So in the top diagram, you've got your waves coming in. They're coming in over nice shallow water, but then they're being sucked out on this area of deeper water, the rip channel. So they are quite dangerous, but the rip channel, you're going to have a lot more erosion happening in there than you're going to have elsewhere on the beach. So essentially, the bottom picture, if you're ever in a rip current, just a little bit of general life skills here, don't try and swim against the rip current. You need to swim to the side, so you've got to get out of the rip current, essentially, not swim against it, otherwise you'll just waste loads of energy and it won't go well. So on a much smaller scale, these are going to form erosion in that one particular part of the beach. Now, you can actually see rip currents. If you go to a beach, look for the waves breaking. If there's any gaps in the wave breaking, watch the water there. If it's being sucked out, then you've actually got a rip current there. When they are present, they're often signposted at life-guided beaches and stuff like that. But yeah, they're going to cause the water to move a lot quicker in that area. So just a reminder about the question I set you on the first one. This is the same question. You might have a bit more information. Yeah, Evelyn, you joining as well? You might have a bit more information after today's lesson, so feel free to amend your answers. Just get that into me by the start of next week. That would be excellent. All right. Cheers, guys. Keep an eye out for the next lesson, which I'll upload some point next week.